2020 has been an illuminating year. I am here to introduce a New Year's resolution for 2021, and that is to minimize my intake of concentrated exhaled breath in 2021. How am I going to do that? I have to define it, establish a unit of measurement, estimate it and quantify it, possibly even measure it, and in the end minimize. I want to minimize my intake of concentrated exhaled breath in 2021. First, to define concentrated exhaled breath, and I'm going to use a paper bag to do it. That is 100% concentrated exhaled breath. Fluid dynamics, biochemistry, particulate dispersion can tell you exactly what's in that bag, but I'm saying it 100% came out of my body, it's 100% concentrated exhaled breath, and I don't want to breathe out of the bag. All right, so I said the bag is 100% concentrated exhaled breath. But what if I have something in the middle? It's not all 100%. So let's say I take this plastic kitchen container, and let's say it's full of exhaled breath, and it's 5.5 liters. And this bin is 41 liters, and let's say I pour the exhaled breath into the bin. And now the bin has 5.5 liters. Out of 41 liters is 13% concentrated exhaled breath, and I ask the question, do I want to breathe out of the bin? It's better than 100% exhaled breath, but 13%, I don't think I'd want to breathe out of the bin all day long.
You can see from the length of the video that we're going to go somewhere with this, and we're going to need some units to do that. So, volume, not gallons. Americans, even if I wanted to, did you know that there is an imperial and a US version of each, a gallon and a quart, and they're different? I will be using cubic meters for the volume calculations, and I will say the result in liters. So I will write it like this, and I will say liters, because that is a liter. A gallon is about 4 liters. A beer is somewhere between 1/3 of a liter and 1/2 of a liter. A lot of products are sold in 1 liter, and in America, sometimes they're sold in 2 liters. Lengths, I will be using meters, and I'll be relating lengths to volumes a lot. So now you know why I'm using cubic meters and the metric system. Volumetric rate, that is a volume per time, so that'll be calculated and written in cubic meters per minute, but I'm going to say liters per minute because that is liters per minute. Time will be in minutes, not seconds or hours, only minutes. So, getting ice cream takes about 15 minutes. 60 minutes is wrong, 60 minutes. A typical class is 48 minutes, 50 minutes, 60 minutes, 100, 108, 110, or 120 minutes. 180 minutes would be a really long class. The shortest movies are 90 minutes. The original Toy Story is 81 minutes. The longest movies are 180 minutes. Godfather 2, Lord of the Rings, and Schindler's List were each approximately 200 minutes long. An 8-hour workday is about 500 minutes. We sleep for about 500 minutes if we're lucky. A flight between the U.S. and Europe, also about 500 minutes. If we are awake for 2/3 of the day, that's about 960 minutes. A full 24-hour period is about 1,500 minutes. So each day, we work for about 500 minutes, live for about 500 minutes, and sleep for about 500 minutes. You get the idea. The minute is a reasonable unit of time, and I'm going to use the minute. This is the equation that I'm using to determine the volume of exhaled breath intake over a time period. The CEB is the concentration of exhaled breath in the space at any given time, times the rate of inhale, and that is a volume per time, so liters per minute at any given time, times concentration is the rate of intake of exhaled breath. Add that up over a time period, and you get the volume of exhaled breath intake over the time period. That looks complicated. It looks like calculus, but really it's just a fraction added up, and the main part of the fraction is the concentration of exhaled breath, which is the volume of exhaled breath in the enclosed space over the volume of the enclosed space as a percent. And if you remember anything from fractions, if the top of one side of an equation is large, the bottom of the other side of the equation is small. So if the concentration of exhaled breath is large, the fresh air is small. Assumptions. I will get through these quickly. First assumption, uniform distribution. Now, what does that mean? That means I am not doing any fluid dynamics or airflow modeling. I am simply asking the question, is the exhaled breath in the room or not? If the exhaled breath is in the room, it distributes throughout the room, it is uniformly distributed throughout the room, and is not concentrated in any one place. Is that a good or a bad assumption? I am simply asking the question, is there enough exhaled breath in the room to concentrate? And you could debate the details forever. Is it optimistic or pessimistic, risky or conservative? It depends on how you look at it, and it could go either way depending on how you look at it. And again, you could debate the details forever. Is it verifiable and accurate? Maybe someday by somebody. I am saying if the air from the bag is in the room, I might be breathing some, and I don't want to breathe the air from the bag. Uniform distribution. Next assumption is the breathing rate, and notice that it appears twice in the equation, once as the inhale and once as the exhale, but I do want to keep them separate. The exhale is the production and the inhale is the intake. I'm using volume, and the volume of the exhale is probably greater than the volume of the inhale simply because the air comes out warm, but I am saying that they are approximately equal. Interestingly, on the mass of the exhale is definitely greater than the mass of the inhale. If you have a pot with dirt in it and it weighs 10 kilograms, and then you plant a seed and the plant grows, how much does the pot, the dirt, and the plant weigh after the plant grows? It weighs more. Where did the mass come from? It's biochemistry. In other biochemistry, watch the TED Talk. This is a good time for a side note. I said possibly measure concentrated exhaled breath, and people do it already. The CO2 in our exhaled breath is harmless, but it is measurable in an enclosed space. CO2 meters, not carbon monoxide meters, CO2 meters, are sold commercially for greenhouse monitors and indoor air quality. Good search terms are CO2 monitor, CO2 detector, carbon dioxide monitor, air quality monitor, or IAQ, which stands for indoor air quality. Check them out. Breathing rate. The normal or resting breathing rate for a 70-kilogram man is 6 liters per minute, and that is what I'm going to use, 6 liters per minute. Discussion around the breathing rate. You can hold your breath for maybe a minute, maybe 3 or 4 or 5 minutes if you're good. The record is 10 plus minutes. Free divers can go over 10 minutes, but we're not holding our breath. Our breathing rate while we're sleeping, less. While we're exercising, the Tour de France was held this year. The numbers I found were 50 to 100 liters per minute, and that really is a lot. But then that raises the question, does the concentration in the room increase linearly with the breathing rate? Do we transfer 10 times as much from our lungs to the air because we're breathing 10 times the volume? I doubt it. Back to the basics. Can you fog a mirror? Then you can fill up the plastic kitchen container in 1 minute. 6 liters. The container is less. Next assumption, the time life of the exhaled breath. Does time sanitize the air in the bag? Now, I don't want to breathe the air from the bag no matter how long it's been, but back to our fractions. If I say the concentration of exhaled breath is the volume of the exhaled breath over the volume of the enclosed space, that is a rate that continues over a finite volume, which is, over time, infinity over a finite enclosed space, which is infinity %, and that doesn't work. So what I said was there is a maximum time for the exhaled breath in a space, and I said that maximum time is 50 minutes. That also means that there is a maximum volume of production for an individual, and that is 50 times the liters per minute, which is 300 liters for a maximum volume for an individual. More possible discussion around that. Does the exhaled breath slowly go away in exponential decay? Does it disappear in random groups? Does it matter forever until it is exhausted actively as a nearly neutrally buoyant substance floating like a glider in updrafts? Does it only matter for a few minutes, dying for lack of resources in its microscopic little vapor ships? Lacking something conclusive? I said 50 minutes. And if you think 50 minutes is long, I'll offer you the bag after an hour and tell me if you prefer that or fresh air. To our first scenario, a Boeing 777 full flight between the United States and Europe, 500 minutes, 368 total passengers, 30 in first class, 84 in business class, 254 in economy, assuming an average ceiling height in the cabin of 1.67 meters, which is 5.5 feet. That's kind of low, but you do have the baggage compartments and the seats taking up volume. Assuming a maximum individual production of 50 minutes, you reach a steady state concentration of exhaled breath after 50 minutes when the passengers have breathed their max production of 16.1%. Each individual passenger on the flight breathes 459 liters of exhaled breath, and the passengers as a whole share 168,400 liters of exhaled breath during the flight. If the exhaled breath did not go away after 50 minutes, the passengers on the flight during the flight breathe the volume of the cabin 1.54 times for a total max concentration at the end of the flight of 154% exhaled breath in the cabin. If you're in aviation and you're watching this, or you just know what's wrong here, you're losing your mind right now, because that is not what happens. It's an interesting scenario, but designers noticed what a problem that would be decades ago, and there is a minimum ventilation requirement. There is a minimum amount of fresh air brought into aircraft cabins. There is a ton of fresh air in aircraft. Ventilation. 14 CFR, which is the Federal Aviation Regulations, Section 25.831, states, for normal operating conditions, the ventilation system must be designed to provide each occupant with an airflow containing at least 0.55 pounds of fresh air per minute. Now, what is pounds in this case? Is that a force? Is that a pressure? Is that a mass? It is a volume in this case, and that brings us to another video, how cabin air systems work. He does the fluid dynamics. He does the airflow modeling. He does the particle sizes. He even does the history of all these things. 20 minutes, came out in March of 2020, almost as if he was anticipating my New Year's resolution. Watch it, 20 minutes, how cabin air systems work. Have you ever smelled a fart outdoors? If you did, that same fart indoors would make your eyes water, and on an elevator, people would be getting off early. The cabin air systems video goes into detail and answers the question. We are not breathing from the bag in an aircraft cabin. But back to our fractions, quantify that a little bit. I said the volume of the aircraft cabin is 716,000 liters, and the rate of exhaust is 103,000 liters per minute. That fresh air rate is enough to replace the air in the aircraft cabin every 7 minutes. So do the passengers ever reach their max production of 50 minutes of exhaled breath into the cabin? No, the cabin air is replaced much faster than that. What does that do to our concentration of exhaled breath? We have a new fraction. We have our rate of exhaled breath produced divided by our rate of fresh air, and exhaust is 6 liters per minute per occupant divided by 280 liters per minute per occupant. So the fresh air rate is 45 times the breathing rate, and our concentration of exhaled breath, steady state, is 2.1%. And that is being pessimistic and assuming uniform distribution, which is not true, and being pessimistic and ignoring the HEPA filtration, which is in addition to all that fresh air. Our new intake per individual is 63 liters of exhaled breath breathed during the flight. Now, that kind of sounds like a lot still. That is more than the entire trash bin. However, keep in mind that each passenger breathes 3,000 liters during the 500-minute flight in total. That is 2,937 liters of fresh air breathed during the flight. That is a lot of fresh air. All passengers combined share a total of 23,200 liters of exhaled breath during the flight, and that definitely sounds like a lot, but keep in mind the passengers breathe 1.1 million liters of air during the flight. That is a lot of fresh air, and the cabin air system purposely localizes the cabin airflow so it is not uniform distribution. We are not breathing all of each other's air during a flight. Are we breathing from the bag? No. In 2021, will I fly? Sure. Concentrated exhaled breath minimized.
If I did, it'd be easy. The air's not moving in here. But then it'd fill up the room and all my clothes would smell and my landlord would be pissed. Better to open a window. Or better yet, go outside. But then all that damn fresh air would be putting out my light. You know what I mean?
Solution number 2, let's try to rearrange the aircraft diagram and see what we come up with. If you were paying attention when I said what the airflow is, it's 103,000 liters per minute. That's 1,700 liters per second. That sounds like a really big fan. Where are they hiding that fan? They're not hiding it, but it is a fan. What we normally call a jet engine is more specifically called a high bypass turbofan, and that means lots of air. Another thing I adjusted on the diagram, the exhaust arrow still points out, and I added a couple more, and those are windows. And this is a building pre-efficiency. Not prehistoric, pre-efficiency. A lot of people know what these are like. They're a little cold in the wintertime, they're hot in the summertime, but they have lots of fresh air. They're not comfortable, but it depends on how bad I want my resolution in 2021. Now, it's not fair to call that building pre-efficiency. It probably uses less energy than the efficiency building. A fair name would be low-energy natural fresh air building, also known as a building that I would spend a lot of time in 2021. Solution number 3 is the best of all of them. Near zero energy used and dollars spent for maximum efficiency, near infinity volume, near infinity fresh air. Outdoors. Zero concentration of exhaled breath, outdoors. I did try to contain it. I tried to put it in the fractions. I tried to concentrate the exhaled breath. And in this scenario, there is a large volume of exhaled breath, but that infinity is on the bottom. I'm rounding down to 0. In summary, if I want to minimize concentrated exhaled breath, the word concentrated is key. What makes these numbers big? Indoors, high density, a long time, and probably a low ceiling contributes. Outdoors, again, I'm rounding to 0. Now that 0% concentration exhaled breath has been up there since the beginning of the video because I wanted to keep track of my concentration exhaled breath while I recorded. But it's annoying because I want to relax and think about other things. Because in the end, it's not about calculus or fractions, volumes, airflows, ventilation. It's not about knowing anything. It's about doing. So when it was raining, I did something else. And I spent a lot of time out here recording. People came over and visited, and it was nice. And we gathered, and the fresh air is relaxing. Thanks for watching. Happy New Year.